The next we continue the methods of establishing the lower bounds in a information theoretic arguments. That means a decision tree. Uh, the information theoretic arguments is the number of inputs or outputs to process an information theoretic lower bound is based on the amount of information an algorithm need to produce to achieve its solutions. A binary search fit here we are trying to find the location of given value in the sorted array. Since we have the array is stored, we can with each guess the eliminate half of the possible location of the goal. If the resulting in the lower bound is a worst case of log n steps. A decision tree or the model of an algorithms operation that can help us to analyze the algorithms such as a search and sort that works by the comparisons. In a decision tree is an internal nodes representation and comparison and leaves the represent outcomes. The tree branches based on the whether the comparison is true or false. The next thing is an advisory arguments. The if the another approaches to finding the lower bound is an advisory argument, this method depends on the advisory that makes the algorithm work the hardest by adjusting the input. For the example, when for the example, when playing the gauging the game to determine a number of between 1 and n using yes or no. The advisory puts the number in the largest of two subset generated in the last question. The text also provides an advisory arguments to show that the lower bound on the number of comparisons need to perform the merge of two sorted n element list into a single 2n element of list. The another thing is a problem reduction. A key idea in the analysis of algorithm in the problem reduction. If we have come up with a way to convert a problem we wish to solve to an instance of the different problems to which we already have to solution these products to produce a solution to the original problem. Suppose we wrote a program to solve some problem of a few days later to find the out of program needs to be written to solve a similar problem to B. To avoid the writing too much new code, you might try to come up with a way to solve B using the implementation of A. So given your input to problem B, you would need to have a produce to transform this input into corresponding input to an instance of problem A. Then solve the instance of problem A which you already know how to do. You need to transform the output of A back to the corresponding solution to B. If a problem reduction can be used to show the lower bound in If problem A is at least as hard as a problem B, then a lower bound of B is also lower bound for A. Hence, we wish to find the problem B. We know the lower bound that can be reduced to the problem A.